content is for educational purposes only, drawing from our professional and educational experiences and opinions. Please use this information at your own personal or professional discretion. We are not liable for anything you do with this information.
Good evening. Welcome to Ask the Lady Electrical Inspector podcast. I am your host, Tabatha L. In this episode, we will examine the most common reasons electrical transition fittings fail inspection. These issues include improper installation methods, violations involving listing and labeling standards, compatibility problems between wiring methods, and frequent National Electrical Code compliance errors. Electrical transition fitting is a specialized connector designed to safely join two different wiring methods or conduit raceways. These fittings create a secure transition from one raceway to another, such as a non-metallic sheath cable to rigid metallic conduit, while maintaining electrical continuity and compliant with the National Electrical Code safety requirements. Why are transition fittings used? Different wiring methods, including NM cable, MC cable, EMT, RMC, FMC, and liquid tight conduit, each have unique physical and installation characteristics. Transition fittings are prefabbed, UL-listed devices engineered to integrate these raceways into a single assembly. By using listed transition fittings, electricians can reduce installation time, minimize material costs, eliminate unnecessary junction boxes, and provide a more durable, protective wiring transition. Most importantly, these fittings help ensure safety and code compliance. Traditional transition methods. Electrically, there are several different methods to transition between raceways. Ideally, these methods have traditionally been made using a junction box, conduit body, or steel heavy wall coupling. Of these methods, the steel heavy wall coupling transition, often called a go-to fitting, is one of the most common used in the field. In this arrangement, two connectors are joined together using a steel coupling to transition from one raceway system to another. Although widely practiced, this method is not approved by many authority-having jurisdictions because the go-to assembly itself is not specifically listed for that purpose. This creates a compliance issue under several code articles, particularly Article 300.15. Article 320.6, and so on. These articles state that fittings shall be used only with specific wiring methods for which they are designed and listed. While these connectors are individually listed for their intended application, the heavy steel coupling itself is listed only as a rigid conduit coupling, not as a transition device between dissimilar raceways or fittings. Mechanical strength and electrical continuity in raceway transition fittings. The National Electrical Code places significant emphasis on the integrity of raceway systems, particularly where fittings and transition components are used to connect different wiring methods. Raceway fittings are not merely mechanical accessories. They are integral components of equipment grounding and bonding systems. As first mentioned in a 2012 Independent Alliance of Electrical Industry article, transitioning between raceways, every fitting must accomplish two essential functions simultaneously. Transition fittings must maintain the physical security and structural integrity of the raceway system, preserve electrical continuity for effective grounding, current return, and bonding. These principles are supported throughout multiple articles of the National Electrical Code and are frequently evaluated during electrical inspections. Mechanical integrity requirements. The National Electrical Code. Requirements for raceways and fittings are intended to ensure that the wiring methods remain securely fastened and protected from physical damage. Article 300.10. Electrical continuity of metal raceways and enclosure. Article 300.10 requires metal raceways, cable armor, and other metallic enclosures for conductors to be metallically joined together into a continuous electrical conductor capable of safely carrying fault current likely to be imposed on the system. This article established that fittings are part of the grounding and bonding path and must maintain both physical and electrical continuity throughout the installation. A loose, improperly threaded, or poorly assembled transition fitting may compromise raceway alignment, mechanical retention, fault current performance, and bonding continuity. Field fabricated assemblies, commonly referred to as go-to fittings, often rely on thread engagement between dissimilar components, not specifically listed for that purpose. The authority having jurisdiction frequently evaluates whether these assemblies provide significant mechanical reliability under Article 300.10. Listing and labeling considerations. Article 110.b. Installation and use requirements requires listed and labeled equipment to be installed and used in accordance with its listing and manufacturer's instructions. This becomes especially important when electricians combine an EMT connector, a rigid coupling, a flexible raceway fitting, threaded adapters, reducing bushings into field assembled transition methods, not specifically identified by the manufacturer as an approved assembly. Even if the assembly appears mechanically secured, the authority having jurisdiction will reject installations where components were not evaluated together as a listed system. Thread compatibility is uncertain. Environmental ratings are violated. Bonding continuity cannot be verified. A fitting assembly that is not installed according to its listing will fail inspection, regardless of whether it appears functional. Bonding and fault carrying path requirements. Article 250.4. A effective grounding fault carrying path. One of the most critical bonding principles in the National Electrical Code is found in Article 250.4 A5, which requires electrical equipment and conductive materials likely to become energized to be connected together in a manner that establishes an effective ground fault carrying path. The code defines an effective ground fault path as permanent, low impedance, capable of safely carrying maximum fault current. Any increase in resistance or impedance at a raceway transition fitting can reduce fault current performance and interfere with overcurrent device operation. Improper field-made go-to transition fittings may create high resistance connections, intermittent bonding, corrosion points, loose thread engagements, and reduce fault clearing capabilities. These deficiencies may prevent breakers or fuses from opening quickly during a fault condition. Corrosion and dissimilar metal concerns. Corrosion is another major concern involving unlisted raceway transitions. When dissimilar metals are joined together without proper protection, galvanic corrosion can develop over time, especially in wet locations, rooftop installations, exterior environments, and industrial occupancies. Corrosions can deteriorate thread engagement, increase impedance, interrupt bonding continuity, weaken mechanical support. The authority having jurisdiction will evaluate whether fittings are listed for wet or corrosive environments, compatible with the raceway material, protected against galvanic reaction. Failure to address corrosion protection may violate both NEC bonding requirements and the manufacturer's listing instructions. The authority having jurisdiction, interpretation, and field enforcement. The authority having jurisdiction commonly evaluate transition fittings using three primary questions. Is the assembly mechanically secured? Is the fitting listed and installed according to the manufacturer's instructions? Does the assembly maintain a reliable low impedance bonding path? If the answer to any of these questions is uncertain, the installation will be rejected. Because the raceway systems frequently serve as the equipment grounding conductor, the authority having jurisdiction must ensure that every fitting maintain continuous bonding integrity from one raceway section to the next. Best practice recommendation: to improve compliance and reduce inspection failures, electricians should use listed transition fittings specifically identified for the wiring method involved. Avoid improvised combinations of unlisted fittings. Verify thread compatibility between raceway components. Use fittings rated for the environment, including wet or corrosive locations. Ensure lock nut, bushings, and bonding components are properly tightened. Follow manufacturer's installation instructions exactly as listed. Properly listed transition fittings help ensure both mechanical strength and dependability, electrical continuity throughout the life of the electrical system. Listed alternatives for raceway transitions. For many electrical installations, listed transition fittings are readily available and are the preferred method for connecting dissimilar raceways and systems. Multiple manufacturers produce UL-listed combination couplings and transition fittings designed for applications such as EMT to RMC, EMT to FMC, RMC to LFMC, NM cable to EMT, MC cable to EMT. These fittings are specifically engineered and tested to maintain both mechanical integrity and electrical continuity in accordance with the National Electrical Code requirements and product listing standards. A listed transition fitting must accomplish several critical functions: securely bonded and connected raceway systems, maintain a low impedance fault current path, protect conductors from abrasions or damage, preserve the environmental rating of the wiring method when applicable, comply with the manufacturer's installation instructions and UL listing requirements. Trade size limitations. The maximum available trade size for listed transition fittings vary depending on the wiring method, fitting design, and manufacturer specifications. For most UL listed metallic conduit transition couplings such as EMT to FMC, EMT to RMC, or RMC to LFMC, the largest commonly manufactured standard trade size is typically 4 inches. However, larger listed fittings may be available through certain manufacturers for specialized commercial industrial applications. Because oversized transition fittings become increasingly expensive as trade size increases, many electrical contractors choose alternative installation methods once raceway systems exceed standard fitting size. Common industry practice. In large conduit systems that require transitioning raceways, contractors frequently install junction boxes, pull boxes, wireways, auxiliary gutters, instead of relying on oversized transition fittings. This approach often provides easier conductor pulling, improved accessibility, better mechanical support, reduced installation costs, greater flexibility for future modifications. However, when boxes or cabinets are used as transition points, installers must still ensure compliance with applicable NEC requirements related to box fill, bonding and grounding, conductor bending space, support and securement, environmental ratings, accessibility. Inspection considerations. The authority having jurisdiction will verify the following during the raceway transition inspection. The fitting is listed and identified for the specific wiring methods being connected. The raceway materials are compatible. Bonding continuity is maintained. Lock nuts and bushings are properly installed where required. Flexible raceways are supported within the distance. The installation follows manufacturer's instructions, field modified fittings, improvised adapters, or a combination of parts not specifically listed together are among the most common causes of failed transition inspections. Another alternative is to use a C-style conduit body fitting with threaded connectors installed on each end. This method can provide conductors access and allow a transition between raceway systems. However, because of the listing concerns, similar to those involving steel heavy wall couplings, the authority having jurisdiction approval is typically required. Understanding thread compatibility. When using conduit bodies or hubs as transition points, thread compatibility becomes extremely important. The two most common thread types are NPT, National Pipe Thread, a tapered thread designed to create a tight seal through thread deformation. The NPSM, National Pipe Straight Mechanical, a straight thread design intended primarily for mechanical connections secured with lock nuts. Most rigid conduit bodies use tapered NPT threads, while many dry location fittings use straight NPS threads. Problems arise when incompatible thread types are mixed. For example, installing a NPSM fitting into a NPT thread hub can result in poor engagement, reduced mechanical strength, and increased impedance. This issue becomes even more significant as the fittings age or become exposed to moisture or corrosion. Wet locations and corrosion concerns. A steel heavy wall rigid coupling use straight threads and generally perform adequately in dry environments when properly tightened. However, steel heavy wall rigid couplings offer limited corrosion protection, especially on the internal threads. Over time, corrosion and oxidation can compromise electrical continuity and increase raceway impedance. Because of this, unlisted go-to assemblies are not recommended in damp or wet locations. A wet location rated conduit body provides better environmental protection and better thread engagement, primarily when used with correctly matched fittings and sealing washers. Rain-tight and liquid-tight fittings must always be installed with the sealing washer included as part of the listed assembly. UL interpretation and industry practice. In a 2010 interpretation, a UL staff engineer explained that conduit body hubs are generally intended for rigid conduit systems. The interpretation cautioned against installing EMT fittings into conduit body hubs because mismatched thread styles can create improper engagement and increase impedance. While this interpretation raised legitimate concerns, field practices have varied. Many electricians and authority having jurisdiction recognize that some conduit bodies are manufactured with thread tolerance, capable of accepting both straight and tapered fittings. Ultimately, acceptance often depends on the quality of the installation, proper thread engagement, mechanical tightness, electrical continuity, and of course, the authority having jurisdiction approval. Practical installation consideration. Before final installation, electricians should dry fit fittings into hubs to verify proper thread engagement and mechanical integrity. A fitting should not easily or be removable by hand after tightening. When transitioning between raceway systems, electricians should evaluate the installation carefully and prioritize the following options: a listed transition fitting, a junction box or enclosure when space permits, a properly evaluated conduit body assembly when approved by the authority having jurisdiction. Steel heavy wall rigid couplings transitions should never be allowed in wet or corrosive environments due to long-term bonding concerns. Authority having jurisdiction and electricians working together. The authority having jurisdiction. We are not here to delay projects. We are partners in ensuring safety, code compliance, and long-term system reliability. When installations are properly planned and executed from the beginning, inspections become more efficient, predictable, and routine. Listed go-to fittings locations that often fail inspections. Common areas include HVAC rooftop units, motors, generators, pumps, transformers, compressors. Electrical equipment that cause vibrations. Flexible raceways are commonly installed where equipment creates vibrations or movement. Rigid raceways connected directly to vibrating equipment can loosen, crack, or place stress on fittings and conductors. Transitioning from a solid raceway to a flexible raceway helps absorb vibration and reduce conduit fatigue, connector failure, noise transmission, damage to electrical terminals. These locations are some of the most common areas where the authority having jurisdiction see transitioning from EMT or rigid conduit to a FMC or OFMC, navigating obstacles and tight spaces. Flexible raceways make things easier in locations where rigid conduit bends would be difficult or impractical. Examples include congested ceiling spaces, tight wall cavities, around structural steel, above hard ceilings, equipment rooms with multiple systems. Using flexible raceways can reduce excessive bends and help installers route conduits and conductors efficiently while maintaining proper support and protection. Accommodating equipment movement. Some equipment requires limited movement, adjustment, or repositioning after installation. Examples include adjustable lighting systems, connected motors, suspended equipment, machinery subject to thermal expansion, removable equipment sections. Flexible wiring methods help prevent strain on conductors and terminations when slight movement occurs. Common flexible wiring methods. FMC, typically used in dry locations where flexibility is needed but moisture protection is not required. OFMC, used in wet, damp, or outdoor environments where moisture resistance is necessary. Common locations include rooftop HVAC equipment, outdoor condensers, car washes, industrial equipment. Common inspection issues. The authority having jurisdiction identified violations included unlisted transition fittings, improper go-to connectors, unsupported flexible conduits, excessive FMC or LFMC lengths, incorrect fittings for wet locations, missing bonding provisions, violation of listing and labeling requirements are some of the things that fail inspections often. As mentioned, areas receiving close inspections often include generators, transformers, motors, rooftop mechanical equipment, high vibration, industrial machinery. Proper transitions between rigid and flexible raceways are critical for equipment protection, electrical safety, grounding continuity, NEC compliance, and long-term reliability. The key takeaway: electricians transitioning from rigid raceways to flexible raceways, primarily when flexibility, vibration, isolation, equipment movement, or installation efficiency is necessary. The transition must always comply with the listing and labeling, support, grounding, and environmental requirements of the National Electrical Code. For example, FMC typically used in dry locations, so FMC wet or outdoor locations, and MC cable commercial branch circuit applications. Selecting the correct flexible wiring method depends on the environment, the equipment type, and the installation conditions. Join me on Wednesday, June the 6th for another informative episode where we will discuss common violations, inspection pitfalls, and practical ways to prevent costly corrections while ensuring safe and compliant installations. If you are looking to expand your knowledge of the electrical standards, code compliance, and industry best practices, consider exploring 60 Best Electrical Podcasts featured by FeedSpot. You can also connect with me on Facebook, Instagram, YouTube under the name Ask the Lady Electrical Inspector. For questions, comments, or future topics, ideals, feel free to email me directly at asktheladyelectricalinspector@gmail.com. Together, we can continue promoting safer electrical systems, stronger installations, and better code compliance throughout our industry. Thank you for tuning in. Until next time, stay compliant, stay safe, and keep the power flowing. Good night.